All right, so we're going to talk about what's going on with the gas, with the molecules in the sample. So we're going to talk about the kinetic theory, and there's 5 statements or postulates. And I was just starting to say that you can actually take these postulates and with appropriate mathematics and physics, you can actually kind of derive the ideal gas law. So these are very sort of intimately connected with the ideal gas law in a way. So first of all, gas molecules are always moving. You've got this continuous random motion thing going on with these molecules. They never stop. And they're also very small compared to the distances between them. And that statement alone actually helps in explaining why gases are so compressible, right? So this really explains the compressibility of gases. Because if there's a lot of room between molecules, then as you compress the gas, you can just take up some of that room. And, you won't be squeezing the actual molecules, you just be having less space between them. The pressure exerted on a gas is due to collisions between the molecules, and also importantly with the collisions of those molecules with the walls of the container. So this is, and the kinetic theory actually, if you were to work with this, you would take the total force of the collisions with the walls and divide it by the total area. And that would give you the pressure. But we're not going to do that in this class. If you like that kind of stuff, you can take PChem and we'll do it there. Anyway, another thing is that gas molecules do not interact in this theory. They're really too far apart to attract each other or repel each other. But this starts to change as they get very close to each other, as you might imagine. And here is a very important postulate. I would say this is the most important one, because it has to do with what happens, or what temperature is really. And this kinetic theory proposes that the average kinetic energy of gas molecules is proportional to the Kelvin temperature. So these brackets are how we write average. Okay, that's average is proportional to the temperature as long as we are in kelvins. So that's kind of cool, right? Because it tells you that as the temperature goes up, the molecules are moving faster. And it also tells you something, it tells you that the temperature sort of measures, we say it's a measure of the average kinetic energy of gas molecules. And that's very important. So what these statements do is they help us understand the behavior of gases. And I'd like to give you an example. I have a video on this, which maybe some of you have even seen, and the video gives more than one example, but I'm just going to give the one example here. And what I'm going to do is I'm going to use the kinetic molecular theory, the kinetic molecular theory, to explain why, if the volume is constant, okay, pressure is proportional to temperature. So look at the ideal gas law. If we have a sample of gas, then the moles is constant. The pressure is nRT over V. If the moles is constant, which it would be in a sample if we're not taking it or letting gas out, and if volume is constant, so if these are both constant, then all of this stuff here, these are all constant. So that means that the pressure would be proportional to the temperature. Okay, so we get this directly from the ideal gas law. It's not one of the laws we studied like Boyle's law or Charles' law, but if the volume is constant, the pressure should be proportional to the temperature. So the question is why? What are the molecules doing? And how does this change when the temperature goes up? So if we have a sample, I'm just going to draw it two-dimensionally, but obviously you would have to have a gas in a box with, you know, dimensions, not just area. So here's your sample of a gas. And let's say you heat this up. So you add heat. But the volume is constant. So, I mean, I think intuitively, you know, you would know that those gas molecules, that pressure in there is going to go up, okay? And, you know, the question is, why does it go up? And so let's think about the consequence of the temperature going up, okay? So let's talk about this consequences of this fifth postulate. And the fifth postulate says that this average kinetic energy is proportional to temperature. Well, what is kinetic energy anyway? Anybody know from physics what the formula is for kinetic energy? We'll call it KE equals. Anybody?
1/2 mv squared.
That's right, exactly right. And where m is the mass of a particle and v is the speed or the velocity. So kinetic energy depends on the speed. So if the kinetic energy goes up, it means the speed goes up. Okay, and so these molecules are moving faster. If they're moving faster, that's going to affect the collisions, right? It affects the collisions with the walls. We don't really care about the collisions with their neighbors, but it affects the collisions with the wall. So you're going to end up with more collisions. But you're also going to end up, because of the greater speed, that you will end up with more forceful collisions. And both of these things happen when the temperature goes up. Okay, more collisions, more forceful collisions. So you end up with a greater overall force of collisions with the walls. And what that means is that the pressure is going to go up. So the fifth postulate explains why pressure increases with temperature. It might not tell you it's exactly proportional, but it certainly tells you why that happens. So the fifth postulate sort of elucidates, explains the PT relationship at constant volume. Okay. All right. Well, if we go and look at that fifth postulate carefully, we'll notice that it doesn't just say the kinetic energy of gas molecules increases. It says the average kinetic energy of gas molecules goes up as the temperature goes up. So I'm just focusing here on this word average. So if in the kinetic theory, it says that the average kinetic energy if in the kinetic theory, it says the average kinetic energy goes up, why do you think we'd have to use that word? Why is this word used? Why is it even here? I guess I could say, well, what does this tell you, sort of imply? What does this imply about the motion of gas molecules, about the speed of gas molecules? And somebody wrote, yes, every molecule has its own speed. That's right. Well, not necessarily everyone has its own speed. I'm sure there are many molecules in the sample that are traveling with the same speed, but the answer really is that the molecules are not all traveling with the same speed. So molecules in a gas sample do not all travel with the same speed. You know, that's not something that you think about in everyday life. You know, I don't know, even me as the geek that I am, I don't walk. I didn't find myself walking down the street wondering about this as a teenager, you know. But it is true that molecules don't all travel with the same speed. We're actually going to do a calculation of the speed of molecular motion today. And I wonder if that'll be surprising to you, but we'll see when we get there. But what I want to say right now is that in a gas sample, there is an entire whole range of speeds that gas molecules can be moving. So in a gas sample, there is a whole range of speeds. Okay. So this is very interesting, you know, because when you have a property that varies in a sample, scientists tend to think about it in a certain way, and we tend to use a certain kind of like mathematical thinking when it comes to samples that can have many different, you know, samples where, like, let's say you have the people in the population, right? The height in the population is certainly varied. It's a property that varies between the members of a population. So I guess I would say, how do scientists handle properties that vary across a population? And what they use to understand such things, they use something we call a distribution function. And, you know, just to show you one that, you know, you're probably familiar with, I'd like to first talk about a height distribution function. Okay, so what a height distribution function would be, it would be the probability of having a certain height. We'll call that P of H, probability of having a certain height as a function of that height. And so what does this curve look like? Well, you know that there's sort of more people with mid-range heights than there are very, very, very tall or very, very, very short people. So the function looks kind of like this. You know, what do we call the shape of this curve? Anybody know what this curve is called? You must know. Somebody knows.
It's a bell curve.
The bell curve. And yeah, it's shaped like a bell. And it's shaped like that because here at these low heights, these are small, these are, if you pick a very small height like this one, you see you have a very low probability. So these heights over here, there aren't that great of a probability that someone would be that short. And also over here where the basketball players are, you know, these probabilities, which are indicated by the Y value of the curve, these are low probabilities of being very tall. And most people are kind of in here, right? This is most people are kind of like in the middle of this curve, right? That's most of the probability. Probability starts to get pretty high over here, goes up and up and up, and then it gets much smaller. So these are really most people have sort of medium heights. Okay, so, and actually right in the center of this curve here, this value of the height, this would be the average height. And in general, this will come out to be a very symmetrical curve. right? That's what a bell curve is. It's beautifully tapered on both sides, okay? Well, while we're here looking at this curve, let me ask you, what is the area under this curve? And why? Well, you could just tell me if you know what is the area under the curve. But yeah, somebody said 1. The area is 1. But the question is, why is it 1? Okay. So anybody have an answer to why it's 1?
Because all the probabilities have to add to 1.
Yeah, exactly. All the probabilities have to add up to 1. So what you're basically doing when you're finding the area under this curve is you're adding up all the probabilities. You're adding up all these little lines for all these different, right? So here you're adding up all the probabilities of being at any height, right? You're summing them all up. And when you do that, you keep adding and adding and adding, the sum is equal to 1, okay? You'd have to add them all to get 1. But anyway, so because you have to have a height, right? You can't have no height. So anyway, that's a height distribution function. And that's a nice looking bell curve. And what I'd like to talk about, of course, isn't the height distribution curve. I want to talk about the speed distribution curve for gas molecules. And this actually has a name. It's called the Maxwell Boltzmann. Boltzmann is one of my favorite scientists. Distribution of molecular speeds. But you don't need to know the name of it. The speed distribution curve doesn't look quite as symmetrical as that height distribution curve. So here it has a fast rise, but then it falls off more slowly. So that's how it's different. Faster rise, falls off more slowly. But you know, it still has that property that, let me just, so this would be P of V, the probability of a gas molecule having speed V, okay? And this is versus that speed. Okay, so you still, if you go to low values, these are very slow speeds. And there's few molecules, meaning you have very low probabilities here. Low probability of extremely slow speeds. And also over here, you have low probabilities of very high speeds. And most of the speeds are kind of like over here, you know, or maybe you could extend this a little more, you know. Okay. So, you know, the exact appearance, the exact mathematical function of this curve is not relevant at all to us here. But what I do want you to get out of this is to know what happens, know what this means, and know how the shape of this curve changes as you change the temperature and as you were to say, look at gas samples that had different molar masses. So basically, how does this curve change? How does a curve change when temperature changes and when molar mass changes? Okay. So the next curve I'm going to show you is at two different temperatures. Okay, so here I have, I didn't draw it myself because I'm terrible at it, but I have the probability of a certain speed versus speed. And this guy here, this is at a lower temperature. So this is low T. And this is at a higher temperature. Okay, so how do these curves differ? So I'd like to take a look. I'm going to pick a slow speed. Like I'm going to go over here and say, okay, what about this speed? Well, maybe make it a little smaller so I can do it easier. So I pick a slow speed. And you could see here's the probability. The blue, this here, this is the probability at the higher temperature of being at this speed. And this, if I extend it up to here, this is the probability at the lower temperature of being at this speed. Okay, so if at a slow speed, let me just write what we see there. We see that the lower temperature curve, that's the red curve, has the greater probability. Why is it not? And the higher temperature curve has the smaller probability. So what does that mean? So it means at lower temperatures, there are more slow-moving particles. Okay, and if I go ahead and do these and look at the opposite situation, well, not really the opposite, but I look at a higher temperature. So here I'm going to pick a higher temperature. Okay, and here you could see this Y value here is a very low probability of the low temperature curve having that speed. So very low probability of the low temperature curve having that speed. And let's compare it to over here. This is the higher probability of the high temperature curve molecule having this speed. So if I put that together at higher temperatures, so this is the high blue curve is the higher temperature curve. Higher temperature curve has the greater probability, and the lower has a lower probability. So basically the conclusion is that at higher temperatures, there are more fast-moving molecules. So let's see what else we got here. Here's the higher temperature. Here's the lower temperature. Here's the higher temperature curve. Okay, sort of more exaggerated. What else can we see in this curve? So the first thing is that, first of all, this is the bulk of molecules here. The bulk of molecules are moving at a slower temperature, at a slower speed. Here's the bulk of molecules at the higher temperature. Okay, so you can see that the bulk, most of the molecules, move faster at the higher temperatures. But there's something else that I want you to notice here, and that has to do with the range. So if I just sort of take the maximum height and divide it in half, I can think about this as a range. We call this the full width at half maximum, but it's just indicative of how wide the curve is, right? So here at the lower temperature, you have a pretty narrow range of speeds. At the higher temperature, you have a much larger range of speeds. Let me get the, so this is the range versus this. So the range of speeds increases as the temperature increases. So not only will you have molecules moving faster, but you'll have a much higher high and a lower low. You just have a greater range of speeds. Well, they all have, they all go down to zero here. So a lower low isn't really true, but it's the curve stretches in addition to just moving to the right. So, so that's the two things that basically happen as the temperature increases. You get, faster speeds and a greater range of speeds. So anyway, let me ask you this question. Why is the higher temperature curve shorter? What is the reason for that? What do you think?
It would be less likely for a greater number of molecules to be moving at the same speed.
Well, you're right in the sense that, these numbers are all pretty small. So each separate speed will be less likely, right? But that's because you have this greater range. Yeah. So, but no matter whether you're at the higher speed or the lower speed, the probability of having a speed is 1. So the thing that's got to be constant here is the area under these curves. And if the area is going to be the same and you stretch the curve out, then the top has to be smaller. So I guess that's really the reason. But what you said was mostly true, actually. So why is the higher temperature curve shorter? And that is because the area must equal 1 for each curve. So they have to have the same area. So if the range is bigger, it must mean the height must be shorter to keep that area the same. Okay, so that's basically the reason. So another thing I wanted to talk about with this Maxwell Boltzmann distribution is what happens as the molar mass changes. So I'm going to just draw you a picture. I'll show you nice, pretty pictures after. So I didn't do a very good job keeping the areas the same, but So what I've drawn here is the same probability curves, but now this is for a greater molar mass, so M, and this is a smaller molar mass. So what happens is that the effect of decreasing molar mass is identical to the effect of increasing the temperature. Lighter molecules move faster. And that's really what this is showing here. On average, lighter molecules move more quickly. So you have the same comparison that you would have for, say, a low temperature and a high temperature with a greater molar mass and a smaller molar mass. So like here, you would say that the bulk of molecules are moving around here at this speed. Here, the bulk of molecules would be moving at much higher speeds, okay? So higher speeds as molar mass goes down, okay? Well, you might imagine that scientists have worked on this, and they have, and there's actually a known formula, a known equation that relates the average speed. Actually, technically, it's not the average speed. It's the something we call the root mean square speed. But you can think about it. It's a kind of average speed. So you could think about it as the average speed, although we call it the VRMS. Okay, the root mean squares. It's actually the average of the squares of the speeds, square rooted. So don't worry about it. You can think of it as an average speed, and it is actually equal to the square root of 3 times a gas constant times the temperature over the molar mass. So it's a very well-known formula, and we actually used this formula in lab last week. So you could see from this formula that as the temperature increases, the root mean square speed goes down. Goes up. And as the molar mass increases, the root mean square speed goes down, because molar mass is in the denominator. Okay, we're going to use this formula to calculate the root mean square speed for, I think, ammonia molecules a little bit later. And I just want to say that this R cannot be in the regular units that we've been using. It must be in joules per mole Kelvin, and that's 8.314. And it's the molar mass actually must also be in unusual units. It must be in kilograms per mole. The reason for this is a joule is a kilogram meter squared per second squared. And so you have to match your units up in order for things to cancel properly. So that's the reason for the kilogram units. So you'll see that when we do that problem a little bit later. Does anyone have a question about any of this? You can always ask. All right, I'm going to show you some prettier pictures of these guys. So what this is showing is basically 3 different temperatures. And you could see that as the temperature increases, your speeds go to higher speed, right? So the bulk of molecules will move at higher speeds. So the speeds tend to increase. We have a greater range of speeds. And you will also see, of course, that the curves flatten because of this. And now actually here's some curves. This is, let's see, at 298 Kelvin. Of course, this would change at different temperatures. But you could see like some of the common gases, oxygen, nitrogen, water, helium, and hydrogen. You could see how their distribution of speeds changes. So this is showing what happens as the molar mass decreases. Okay, and again, as the molar mass decreases, you have greater speeds, you have a greater range of speeds. And then you see this curves flatten to keep the area the same. All right, so So I wanted to talk a little about diffusion and effusion. So this was the topic of part of the lab last week, had to do with diffusion. Diffusion has to do with the mixing of gases, all right? So if you open up a jar of ammonia on one side of the room, I like to use ammonia because it's really smelly, that the odor from that ammonia will eventually go to the other side of the room. It doesn't make a beeline from one side of the room to the other, but it gets there, okay? And the rate of diffusion, it's a movement of particles, mixing of different particles. For example, ammonia mixing with air is actually proportional to that speed, that what we call the root mean square speed, VRMS. So that means that the rate of diffusion is proportional to 3 RT over the molar mass. And so it's proportional to 1 over the molar mass, the square root of the molar mass. This is the rate of diffusion. But then there is a very closely related process called effusion, which I talked about. I'm sure Mrs. Sayok talked about it too, which is if you have a higher pressure here and a lower pressure here, and it is the process by which particles move through a small opening from a higher to a lower pressure region. Okay, and the rate of effusion is also proportional to the root mean square speed. So it's proportional to 1 over the square root of the molar mass. So that means that depending on the gas, they would have different rates of going through this process. And what we did in lab is we looked at the time of effusion. And so that time was proportional to the square root of the molar mass, because time and speed are inverse, time and rate are inversely proportional. So that's basically something that we handled in lab last week. But what I wanted to do is tell you, or to propose the question of what use is effusion? And one of the reasons that I even talk about effusion is because I can tell you about some very unusual or very sort of weird way that uranium was enriched for many, many years. This was the way that uranium was enriched. So I don't know, maybe if you've heard of the Manhattan Project. That was in the 1940s during the war. This was basically the building of the bomb. And whatever you think about that, the way that had to be done was you needed uranium. But uranium is not it has a very tiny percentage of the kind of uranium that's needed, which is the radioactive uranium. So there's two main types, okay? You have uranium that's got a mass of 235 and uranium that has a mass of 238, and they differ in the number of neutrons, right? They have the same electrons, the same protons. But anyway, U-235, this is the radioactive one. And this is 0.7% in nature. We call that the natural abundance. Whereas the other one is 99.3%. You might look at that and say, I'm never going to get anywhere with this. How am I going to use this stuff if it's only like less than 1% available in nature? So anyway, it's too low to use. So in order to use it, you need to enrich. They call it enrich. the uranium. Okay, and I don't know what percentage it has to go up to be usable in a bomb, but I know it has to go up significantly from 0.7. So how are you going to do this? Well, many different methods were thought about back when they needed this stuff for making the bomb, and the one that they settled on, I mean, I just think it's kind of like so out there that they would even consider this. But not only did they consider this, but they did it. They built it, and up until maybe not that long ago, maybe like I think even in 2017, they were still using the method of effusion to enrich uranium. Well, by then they were also using other methods. Anybody know what's used today to enrich uranium or any of these things? Anybody know? When we talk about Iran, and they have a certain number of this piece of equipment, you know, you hear about that. Anybody?
Do they use lasers?
No, they haven't figured out how to do it with lasers. Nope, not yet. How about this? Centrifuges. They have gas centrifuges. All right, gas. This isn't a gas. Uranium is a mineral. It's found in solid ores. So, you know, like rocks. So how would you? Okay. Anyway, how do you even make it into a gas? Well, that's why this whole phenomenon is so bizarre. How they did this. So what it starts with is the fact that the speed of a gas effusing is proportional to 1 over the square root of the molar mass. And the molar mass is different for, okay, first of all, it's different for the two forms of uranium, right? One is 235 and one is 238. But before you can even enrich this uranium, you've got to make a gas out of the uranium. And the gas that you could make from uranium is UF6. UF6 is a gas. So they made some chemical reaction to form UF6. And so in a sample of UF6, you've basically got 0.7% UF6 that's made with U235, and you've got 99.3% of UF6 with U238. Okay. And so they made this gas, and then, okay, they say, okay, well, we're going to take that gas and we're going to put it, oh man, what's going on here? We're going to put it in an effusion apparatus. So they'll have the mixture of 238 UF6 and 235 UF6. And what's going to happen is that the 235 UF6 will effuse faster. Will it effuse a lot faster? No. Let me go through a few slides I have to show you on this, and it'll, first of all, yeah, well, let's go ahead and do it. So this is the picture I kind of drew. This is effusion, and the effusion rate, the root mean, this is VRMS, is the square root of 3RT over M. So if I want to know what is the rate of effusion, what is the ratio of the rates of two different gases, gas 1 and gas 2, I have, what is the rate of 1 over the rate of 2? Well, each of these rates is proportional to the square root of 3RT over the molar mass. So this would be 3RT over M1, and this would be 3RT over M2. Well, you know, if you have a square root like that, you can make it look, you can take it over the whole thing. And then basically all of these things cancel, but now you're taking 1 over m1 dividing by 1 over m2, and you end up with the square root of m2 over m1. So the rate ratio for these two gases, you have to reverse the molar mass in that square root. Now, getting back to our uranium example, we have two gases. We have UF6 with U235 and UF6 with U238. So what is the mass of this? It's 235 plus 6 times 19, right? 19 is the molar mass of fluorine. That comes out to 349 grams per mole. This guy is 3 more. It's 238 plus 6 times 19, or 352 grams per mole. Okay. So so look at these different molar masses. They're almost the same, and that's why this is so hard to do. So what scientists did back in the 40s, I've said these things already. Okay, you put the radioactive substance in the gas phase, and it was converted to UF6, and then we have these two different molar masses. We have 352 for U238 and 349 for U235. So when we want to look at the ratio of the rates, how much faster is one going to get through that opening than the other? Are we going to end up with totally enriched UF6 after going through one chamber? Like if you just do this once, you go through this thing once. So if you go through that once, the ratio of the rates is the inverse, right, of the ratio of the molar masses, and it comes out to 1.0043. So what that means is that the rates are almost the same, that the UF6 with 235 is effusing basically 0.43% faster. If it was 1, it would be the same. It's a little bit faster, 0.0043 faster. That's 0.43% faster. So, here scientists were, trying to figure out how to enrich enough uranium. And that's the kind of math that you're up against. You really can't change that, right? So what they did was they came up with a system. Basically, it was many, many, many chambers. And this is kind of a ridiculous graph, but you can imagine that, you're fusing through each one of these chambers. And for each chamber, you get a 0.43% enrichment. And how many times do you have to do that to get the uranium to the enriched level that is needed? So this is actually a cartoonish kind of picture of what was really done. So they took high pressure UF6 gas, flowing through here. The larger red dots are the U238. The smaller green ones are the U235 F6. So you could see that here you have a lot more red ones than green ones. And then these arrows here show effusion through these openings. And you can see you have more green ones here. But this would have to be done over and over again. And I'm going to show you the picture of where this is done. Well, this was done in Oak Ridge, Tennessee. Oops. Oak Ridge, Tennessee. And look at that. Look at how many buildings. Look at this building. It covered quite a number of acres. Let's see. 4,000 stages. That means there were 4,000 of these like openings like this. 4,000 of these. Okay. And it took 43 acres. So, I mean, this was like, talk about a really large undertaking to make the bomb. It was not, and this was only one small aspect of what was involved with that. So anyway, that's how it was done. I don't know if you were interested in that story, but I always find that's one of the things that I find kind of fascinating about, things that scientists have done that I would have thought, no way, that can't be done. So when you think, no way, that can't be done, you should think again, because people do things that a lot of people think can't be done. Anyway, so I'm going to show you a little video, a couple of videos, because I want to show you the difference between ammonia and hydrochloric acid. So I'm leading up to a demo that shows the different rates with which these gases move. And it's a kind of a nice little demonstration. And it starts with thinking about what happens if you have ammonia and HCl gases. If they come together, they actually form a solid, ammonium chloride. Okay, so the first video talks about the forming of ammonium chloride between these two gases. And I just want to tell you that it is ammonium chloride. The person in the video calls it ammonia chloride. So, oh well. And the other thing is that the person in the video calls these molecules, these are not really molecules because they consist of ions. They're not, there are no there's no covalent bonds except within each of these separate, except within the NH4, which is a polyatomic ion. So it calls it a molecule, but that's okay. They're just particles. And then the second video talks about, well, let's just watch the first one first. So I'll try to do that, that thing next. Let's see if I can get that video going. See, it's always a challenge. Lost my controls again. I just love that. Hold on. Okay. Do I have an echo now? No. Okay. All right.
Hydrogen chloride and ammonia are gases at room temperature. They are highly soluble in water. Dissolved molecules easily pass into air from the concentrated solution. In the gas phase, molecules readily extend beyond the vessels. Ammonia and hydrogen chloride vapors are colorless, but when mixed together they form white smoke. Let's take a closer look and see where this smoke comes from. Smoke consists of small particles that we can't see with our eyes, but plenty of such particles form a plain gray background. Small crystals of ammonia chloride play the role of smoke particles in our case. Let's see how these crystals were formed. We need to zoom in 1,000 times greater to visualize separate molecules. Now we can observe molecules. There are not only molecules of ammonia, hydrogen chloride, and ammonium chloride, but also plenty of oxygen and nitrogen molecules from the air. We won't consider them anymore because they have no interest for us, as they don't react with anything else here. Let's see how ammonia and hydrogen chloride combine. The nitrogen atom in an ammonia molecule has a lone electron pair that can be easily shared with hydrogen in hydrogen chloride. This new molecule is called ammonium chloride.
So I just wanted to say the nitrogen is this blue atom here, and then there's the 3 hydrogens here, and then this is the hydrogen of the HCl, and this is the green thing is the chlorine. So this is the NH4. This is the, oh, you see N, and then there's 1, 2, 3 H's, and then a fourth one here, and then a Cl. So that's the NH4Cl.
Chloride. Separate molecules of ammonia chloride combine together to form a crystal. A small crystal nucleus grows bigger and bigger as new molecules of ammonia chloride join to it. Sometimes a couple of small crystals combine together, giving a greater one. These new crystals can combine in their turn, and so on. This process continues until particles become several thousandths of a millimeter in diameter. These particles form the smoke that we can see. The process of particles growing doesn't stop at this stage. However, growing larger, they become too heavy to fly in the air with ease, and they accumulate on the surrounding surfaces as white powder.
All right, I think that's enough. Okay, so that talks about how if you have ammonia and you have HCl gases and they come together, they're going to form this white, smoky looking stuff that's really solid ammonium chloride. And so now what I'm going to do is show you another video, which doesn't have any sound. I'm going to have to do the voiceover. But what's basically happening in this video is we're taking concentrated HCl and concentrated ammonia and dipping cotton wool, they call it cotton wool because it's England, basically cotton into each of those concentrated solutions and putting them at the ends of a long tube. And basically what you look for is when they come together, when those two gases come together, there'll be a white line on the inside of the tube, which will be for ammonium chloride. That's what means that the ammonium chloride formed there. And that will be where they met each other, okay? And they diffuse, sorry, this is diffusion. They diffuse with different rates, and you could see by where that white line forms, which is moving faster, the ammonia or the HCl. Okay, good, I can do this new share here. What the heck is going on with that? So this movie has some really strange captions. It's trying to describe those cotton things, and it's just, anyway, so this is demonstrating what I've been telling you about. So basically the person here is taking concentrated hydrochloric acid and putting it in a beaker. And she's doing it in a fume hood because it really is like, it literally hurts your nose to inhale this stuff. It hurts. So you have some concentrated ammonia and you have some concentrated HCl, and then basically you wrap cotton around like a Q-tip or something. And then, so here you drop one into the HCl, the cotton, and you drop one into the other one. And you can see there's some stoppers on the other end. That's what's used. We'll shove these into a tube. So there's the long tube. And on one side, what's going on? Yeah. So this is great when you have two people. If you try to do this yourself, you never do it at the same time. So what we're looking for is a white line, a white region is going to form. There it is, okay? And you could see from the position of the clamp, this is to the right of the clamp. And if they go back out again, otherwise I'll have to do it, hold on. So that's the ammonium chloride that forms in the middle. And when you measure it, you could see, they're showing you here that it's about 18 centimeters from the hydrochloric acid end and about 25 centimeters from the other end. So it's over here on the HCl side. I'm just going to go back a little bit. So it's kind of, I think from the position of the clamp and where the white line was, it's got to be somewhere over here. I can't really see it though. Can anybody see it? Anyway, so what this thing showed is that where the white line shows up, it's about 18 centimeters from the white line to the end, and about 25 centimeters on this side, which would mean that the ammonia moved further than the HCl did in the same amount of time. All right, so what we're going to do next is we're going to actually calculate this, calculate how much faster the one is moving than the other. Okay, so let me all right. So if we go to this, this problem one, these are the kinetic theory problems. Problem one, we're going to do after we do two. So let's go to two first. And this is to calculate the relative diffusion rates. In other words, the ratio of the rate of one to the rate of the other. And I always put the lighter one on top because it's moving faster and I want my ratio to come out greater than one. So this rate here, this ratio of the rate, so the rate is proportional to 1 over the square root of the molar mass. So the rate of NH3 over the rate of HCl is equal to the square root of the molar mass of HCl over the molar mass of NH3. Okay, and the molar mass of HCl, right, that's just, well, chlorine is 35.453, hydrogen is 1.008, and that comes out to, well, let's just call it 36.46. How about that? And the molar mass of ammonia is 17.03. So this is the square root of 36.46 over 17.03, which is 1. Let's see. Get another sig fig. Ooh. 1.463. So what that means is that NH3 is moving 1.463 times, or a little less than 1.5 times as fast as the HCl. So if you have a tube, you know, if HCl moves this much, the NH3 will move 1.5 times that much. So like this much, right? 1.5. And then you see your white ammonium chloride over here. If you started with NH3 on this side and HCl on that side. Okay, so that sort of explains that. All right. Well, what I want to do next is just touch on what we're going to be doing in the next unit. Sort of try to maybe introduce it to you a little bit.
Can you go back so I can take a picture of it?
Oh yeah, sure. Sorry about that transition there. I do post my notes though, so you don't need to take a picture. You can just go look them up later.
Yeah, but I have back-to-back classes, so okay, thank you.
Okay. Um,
Lisa, I also had a question.
yeah.
How do you know which one goes on top? Like, how do you know that NH3
Well,
goes?
you know, I
on
don't
top?
like things that come out less than one, you know, because then I
Okay.
have to say this, you know. So I know that the lighter one is gonna move faster. And the heavier one is slower. So I know that the rate will come out greater than 1 if I put the heavier one on top.
Okay.
That's why I do that.
And that's always the
If I had
goal,
done it
right?
the other way, you would have gotten, it's perfectly fine. You would just take it's be the reciprocal of this. It would end up 0.683. And then you would say, okay, HCl is moving 0.683 times as fast as NH3. So it really doesn't matter which way you do it. You just have to know how to interpret it. See
Okay,
what I'm
thank you.
saying? Yeah.
I have a question.
Yeah, good.
What is M?
What is M?
Yeah.
It's the molar mass.
Oh, that's a molar mass? All right, thank you. I thought it was like a weird little thing, but all right, thanks.
All right. Any other questions? No chats either. All right. So, you know, we're really done with the gases. I just have a couple more words to say because we're heading into liquids. And I would say that gases behave ideally, which means they obey the ideal gas law, right? Under most normal conditions. But, you know, I've mentioned before that if you cool a gas a lot or you pressurize it, so in other words, at very high pressures or very low temperatures, okay, then you start getting some interesting developments, right? Because then gas molecules, they get close. Because if you decrease the temperature, you're going to decrease the volume. If you increase the pressure, you're going to decrease the volume. So these things squeeze gas molecules together, okay? And what happens is they begin to attract one another. And what ultimately happens, so the ultimate consequence of this, as I've said before, is they form liquid. Okay. And it's these attractions between molecules in the liquid that, first of all, those attractions, it's the attractions between molecules that make liquid happen. Okay. And then once you have a liquid, these attractive forces determine many, many of the properties of that liquid. So attractions between gas molecules at low temperature and high pressure is what makes liquids form, but also these attractions are responsible for liquid properties. Okay, so you know, back in Chem 103, at least at the end of the semester, we talked a lot about bonds. We talked about bonding, and we talked about basically why, you know, those bonds are forces between the oxygen and the hydrogen, say in this case. These covalent bonds, they're very strong forces of attraction. But now we have a different focus. And instead of focusing on the bonds as we did in 103, now we're focusing on attractions between molecules. So, for example, here you have a polar molecule. I'm going to go over that. I'm going to go over polarity because it's very important for this unit. We have a slight difference in charge here. These deltas are small charges. So a delta negative is a small negative charge, delta positive is a small positive. So we get attractions here between the delta negative and the delta positive on different molecules. You get attractions here. And these attractions are what's responsible for many physical properties. We call these attractions between molecules. We call them intermolecular forces. These guys, these attractions between atoms within a molecule, you could think of these as intramolecular forces. So when I say IMFs, I'm talking about intermolecular forces. And we learn a lot about these in this unit. But you know, I'm not gonna launch into this yet. You know, this is what we're going to start doing, but not quite yet today. For today, I want to take a look at water molecules, and I want to sort of consider how strong are these bonds between the O's and the H's. So you know, you take classes, you take chemistry classes, and teacher tells you different things, and I could tell you what the bond strength of an OH bond is. I could tell you it's 467 kilojoules, but it's not really something that you can reach with your mind. You know, you want to think of how can you compare the strength of these bonds to something that maybe you can picture. So I came up with this example. I basically want us to figure out how much energy would it take to break all the bonds in 1 gallon of water. And I want to compare this to the energy generated by one of those giant turbines. So what I want to do is calculate this and then figure out how long the blades of this turbine, wind turbine, and I have a particular wind turbine picked out, and I'm going to show you how long the blades of a wind turbine would have to turn in 10-mile-an-hour wind in order to generate that much electricity, in order to generate that much energy in the form of electricity. You know, this is a kind of calculation that I don't want to spend forever on it. You know, I don't want to do it exactly. And so when people in science, at least it's an old-fashioned term, but I want to tell you about it. Oh, here's a picture of the wind turbine. Look, these are 130 feet, these blades. That's how long they are. So you can see, look, what we got here. We have a bunch of people. See those teeny people down there? Those are the people that are watching these turbine blades, okay? And you could picture, what is the size of a gallon of water? It's like a dot if somebody was holding a gallon of water. So I want to compare the energy to break all the bonds in a gallon of water to the energy generated by these turbines. How many minutes or seconds would they have to turn to generate that much energy. And this type of calculation we call, because I don't want to do an exact calculation. I want to do what we call the back of the envelope calculation. Now, why is it called the back of the envelope calculation? Because I don't know, nowadays we don't get as much snail mail as we used to, but bills still come and you get plenty of envelopes. And if you're in the kitchen and you're thinking, oh, I really want to calculate that, but I can't do it in my head. And you grab the first thing and you grab the National Grid bill and you turn and you do your calculation on the back of the envelope. And so you just estimate things and you don't pay too much attention to significant figures. So that's what I'd like you guys to do. Here's the back of the envelope calculation. So on one hand, you're going to calculate the energy required to break all the bonds between oxygen and hydrogen in 1 gallon of water. And I'm going to give you everything you need to calculate that. And on the other hand, you're going to figure out how long a wind turbine would have to turn. Now, so I looked up information on a particular wind turbine, and I decided to use this particular wind turbine here, okay? The giant wind turbine Vesta V90. And let's see. This giant wind turbine generates 250 kilojoules of electricity per second if the wind is 10 miles per hour. Okay, so that's what I assume in this calculation. But how are you going to figure out the rest of it? The energy required to break all the bonds between O and H in 1 gallon of water. Well, one thing you need to know is given to you here. You need to know that in order to break 1 mole of bonds, the bond energy for the covalent bond between O and H, this is the energy needed to break 1 mole of these bonds. And it's 467 kilojoules per mole. So what do you have to do in this problem? You start with a gallon. I said 1 gallon, right? So you have a gallon of water. And what are we trying to get to, right? We're trying to, so this is what we start with. And we need, okay, what we need is the energy. This is what we want to find to break the bonds, but we have that energy per mole. So we need the number of moles of OH bonds. So, okay, so that would mean we need the moles of H2O. Well, that means we need the grams of H2O. And then you could see how I'm going to get to the gallon here, right? Because I'm going to go from milliliters and then liters and then gallons. So if you're going the other way, right, you really want to go this way. You pretty much have to go from gallons to liters to milliliters to grams to kilojoule to grams to moles to kilojoule to moles of H2O to moles of OH bonds to kilojoules. So that's kind of the roadmap for how to figure that part out. And then it basically talks about the other part. What you have to do that is right here. Okay, so once you get that energy and you know how much energy is generated per second for the turbine, you can do that as well. So, so what do you think? You think you can do this? Let me have a poll here. How many people think they can do it? Let's see. Give me the thumbs up if you think you can do it. See a few thumbs ups there. Is there a thumbs down? All right, so this is what I think I'm going to do. I think I'm going to open up some breakout rooms, but I'm not going to put people in them. I'm going to try having people put themselves in them. And people who are completely lost, just stay in the main room and I'll get you started. How's that? What do you think about that?
That works for me.
I think that's a good read. Let me see. I've never done breakout room. Assign. Let participants choose the room. We'll have. I'll just make like 4 rooms or 5 rooms or something. I've never done this before. Okay, so there's these breakout rooms. If you have some friends, you want to. I don't know if you know anybody in the class yet, but I think what you should do, don't go immediately into the rooms unless you've already done it. Look at the problem, think about it for 5 minutes and ask me some questions if you have them, okay? If you do go into a breakout room, send me a chat with what you get for an answer, okay? So we can communicate back and forth, all right? I'll check out the chats. But if you don't know what you're doing, you know, stay in this room and I can help you. Well, nobody's going into the breakout rooms. No, to stay for the 5 minutes and look at the stuff. So I'm gonna just let you think about it for a few minutes. You could take a little break and then come back for the last 20 minutes. If you have a question, just shout it out.
How do you find the moles of the oxygen-hydrogen bonds?
How many of them are there in one molecule?
Oh, I see.
Good.
Would you be able to just scroll up a little bit so I can see the numbers?
Oh yeah, sure.
I just didn't get to write them down. Sorry.
I'm using the wrong mouse, so it's not working. Okay, so you want to see this?
Yeah, I just need to see that really quick. Thank you.
No, I'm just going to leave it here
Oh, word. That works too.
because I don't know if everyone got to print it out or download it or whatever. I did send it to you today. So you can also look at your email. It should be there. And it's also posted.
You are going to go over how to do this at the end, right?
I don't know if I'll have time to, but I will post the answer for sure.
Okay,
Yes,
thank you.
Yeah, I could do that.
Thank you.
All right, I think I'm going to start to get people started on this. Well, I see 4 people went into breakout rooms. Okay. All right. Okay. So what we're doing here, right, is we're starting with 1 gallon of water. And what we want to get to is, you know, in a gallon of water, we have a lot of these water molecules, and each bond, to break each bond, well, we want to get to the total energy to break all the bonds. Okay, and we're given a very special number here that should really help us out. And that is this number in the box, this particular one, 467 kilojoules per mole. That is the energy required. So 467 kilojoules per mole is the energy required to break 1 mole of OH bonds. So that's a very important number that we know. So how are we going to get from 1 gallon of water? We need to know the number. Let me just erase this, it's not very elucidating. We need to get to the number of OH bonds, or a number of moles, I should say, of OH bonds in this gallon. And once we get the number of moles of OH bonds, what are we going to do with that number to get the energy required? I'm asking that as a real question. If I know the number of moles of OH bonds, how will I get to the energy needed?
Do you multiply it by the 467 kilojoules per mole?
Right, I'll take the number of moles of OH bonds and multiply it by 467 kilojoules per mole. The moles will cancel, and I'll end up with kilojoules. So that's really the last step in this process. So how are we going to go from a gallon of water to moles of OH bonds? Well, I give you some other information in here. What's the next thing? It says, and it gives you a strategy here. It tells you to go from gallon of water to liters of water, to milliliters of water, to grams of water, to moles of water. All these things are conversions that you know how to do. So that's what we're going to do. We're going to go from gallons to liters, to milliliters, to grams of water, to moles of water, to moles of OH bonds, and finally the last step. Okay, so this just looks really daunting, but if I start with 1 gallon of water, what am I going to put in here to convert to liters? And look at the sheet of paper.
At the top, wouldn't you put 4 liters and at the bottom put 1 gallon?
4 liters, 1 gallon. See where we're going with this? And we're not worrying about sig figs either, because it's the back of the envelope calculation. Okay.
And then it would be 1 milliliter and then 1,000 liters.
That's right. That's right. Exactly. I just have to respond to this chat somehow. Oh, I'm on the wrong. Think about what to do next. Okay, so if I now, I'll be at milliliters. How do I go from milliliters to grams for water?
Aren't they equal to each other?
They are. It's 1 gram per milliliter, at least to a first approximation. So that's not going to change anything. Now, how are we going to go from grams We're at grams now. We got to get to moles. How many grams in a mole?
We're going to divide it by the molar mass of water.
Yeah, let's just call it 18. We could even call it 20 in the back of the envelope calculation. So this is going to give the moles of water. So now how are we going to go from moles of water to moles of OH bonds? How many moles of OH bonds are there in 1 mole of water?
2.
Did you say the answer? I think you did. Say it again.
Is it 2?
2. Okay, so now let's just multiply and divide here. It's really 1 times 4 times 1,000. We're not there yet. We have to multiply by this, but I don't have any more room, so I'm going to multiply now. Okay. Something is right. So that's 444 moles of OH bonds. Okay, so now you know what to do. You have to multiply that by this number, the kilojoules per mole. I'm just going to round it because it's the back of the envelope calculation. So now what am I going to do? I have to go back and look at some information, some additional information. And the additional information that we need is that this turbine, the wind turbine, generates 250 kilojoules of electricity per second at wind speeds of 10 miles per hour. So I would like you now to figure out, if we have to generate, if this is how much energy we want, how long would this wind turbine have to operate? How many minutes? Okay, so I'm really almost done with this problem, but I want you to finish it, okay? Okay, so somebody figured it out, definitely. So how you do this is you go 210,000 approximately kilojoules. This is what's needed to break those bonds. And then we know that the turbine gives 250 kilojoules for 1 second. And that there are 60 seconds in 1 minute. Oh, what a time for this to crap out, huh? Oh, well, I'll have to tell you the answer because oh, here it is. It's coming back. Good. 60 seconds, 1 minute. Okay. So I use dimensional analysis to do this problem. I cancel kilojoules, I cancel seconds. And so 210,000 divided by 250 times 60 comes out to about 14 minutes. Okay, well, I don't know about you, but I find that pretty amazing. You know, you've got this giant wind turbine with blades that are 130 feet and people standing there like this, and the gallon of water is like a dot. And to break these bonds, it would take 14 minutes to generate that much electricity, to generate that much energy. To break bonds in that tiny little gallon. I don't know. What do you think? Do you think that that's kind of crazy? I think it's amazing. But, you know, that's just me. Anyway, if you want to hang out and ask me questions about this or anything else, go ahead. Otherwise, I'm done with what I was going to present today. And some of you I'll see in lab tomorrow. Please read the 2 handouts I posted on the copper week 2. And if you have any questions, just like I said, just stick around.